Thanks very much for coming to our presentation today. The topic of today's presentation is Linux storage system bottleneck exploration. We had a little project and we would like to share with you the results. My name is Zoltan Szubbocsev and my colleague's name is Huo. You can see our email addresses here if you have any further questions after the presentation. Then please feel free to just send it to us. The outline of the presentation is the following. We're going to start up with a little bit of introduction about ourselves, who we are, where we come from. Then this is going to be followed by a description of the methodology that we used in this study, followed by the presentation of the results that we've observed or got on an eMMC stack. And then we're going to move on to something more interesting or more relevant for today's systems. We're going to show you the comparison results that we've received on comparing UFS and NVMe. And this is going to be concluded by a short summary, and then we open up for questions and hopefully some answers as well. Okay, so let's start with the introduction. We actually come from Micron. I would like to ask you to lift your hand if you know Micron, if you've heard about it. Oh, great. Okay, that's what I was expecting. It's one of the greatest, biggest, and greatest storage and memory producer. So both of us work for Micron. We are a part of the embedded business unit. There's several business units. Micron is composed of several business units, and we are part of the embedded one. That's why we are here today. In the last couple of years, our work has been focusing on embedded storage software. And both of us are based in Munich. None of us is German, but we are based in Munich. And we are part of the embedded system architecture and engineering group. A lot of our work is actually, we do a lot of work with automotive customers, and that is the reason why we're based in Munich. Areas we work on: embedded file systems, eMMC, UFS, NVMe, you name it, we've seen it and we've done some work on it. Okay, what is the reason why we're here today, and what is it that we try to achieve with this project? I think the embedded storage is developing at a very fast pace. And there's a lot of questions regarding the system level performance. And about a year ago, I started to search the literature, and I really haven't found anything that answers the questions regarding system level performance in a satisfactory manner. And for this reason, we decided to kick off this project. And the questions that we wanted to answer are the followings. We wanted to understand how much a physical speed on a device, an eMMC, UFS, actually gets translated into system level performance. And we wanted to quantify the Linux storage stack impact on the overall user space performance. Something more interesting, and we wanted to do that for eMMC, UFS, and NVMe, but later on, there's a lot of discussion today in the embedded storage space about NVMe and UFS and which one's better, which one's going to give you a better performance. So we thought, okay, why don't we just try to quantify the NVMe storage stack improvements over a UFS storage stack. Everybody claims that NVMe is better because the storage stack is leaner, much more efficient, but nobody actually gives numbers. How much better it is. So, but this is difficult to do, right? For one reason, you have to have an eMMC, an NVMe device and a UFS device that are performing exactly the same. To be able to do apple-to-apple comparison, you have to have two devices that are equivalent. This does not exist in the real world. So we developed a methodology, and hopefully I managed to convince you guys that it's a valid one that allows us to compare the two, even though we don't have two equivalent devices. And these are the questions that we will try to answer today to some degree. Okay, for those of you, I'm going to ask another question. Is everybody in this room familiar with the three technologies, so eMMC, UFS, and NVMe? So lift your hand if you are. Okay, that's about a third of the people. So without going too much into details, I want to just give you a feeling of how fast these devices actually are. So all three devices are actually, I call them solid-state drive. Probably SanDisk folks or WD folks would disagree with me whether eMMC can't be called a drive, but I call it a drive. And it's essentially, it's basically a bunch of NAND chips, a controller, and some firmware put together, plugged into an embedded system. You have some, storage stack on top, and there you go. You have your storage. Now, eMMC is in HS400, and don't care about the the naming. It runs at about the interface speed. It runs at about 400 megabytes per second. So it's rather fast, and the next generation potentially is going to go up to 566. UFS stands for Universal Flash Storage. In Gear 3, you can run 728 megabytes per second per lane, and you can actually use 2 lanes. So if you do the math, it can go pretty fast. NVMe in Gen 3 is about 1,000 megabytes per second. I'm not sure. It's around that per lane. So, and you can use up to 4 lanes. So you can have a very fast storage device in your embedded system. So takeaway, these are all storage state technologies consisting of a controller, a bunch of NAND, firmware, and they're pretty fast. So now I'm going to give Bean the opportunity to actually show or talk to you guys the methodology that we used in this study.
Okay, hi, my name is Bin Huo. Now let me give you a general introduction how we measure the Linux stack latency. Okay. Here, the benchmark workload generation, we used FIO flexible IO tester. It's a very good performance tester benchmark. Here, we mainly focused on 4K random read at the write and 128 KB sequential read write. For IO mode, we only focused on direct IO and single IO rather than async mode. For the utility of the tracing, here we used Ftrace and block trace. I think in this room everybody knows that. For block trace, it just tell you what happened in block layer. But after and user trace point through block and trace message, this record, it also can trace at the mirror block layer at the host driver at hardware transfer latency. For Ftrace is relatively more complicated, so it can trace and mirror every layer depending on your configuration. Here, one point I want to say that in order to reduce overhead coming from trace itself, for Ftrace we only picked several key function and disabled EST4 file system journal function. So in order to make sure your overhead should be make sure under 5%. Okay. Okay, this slide is shows the Linux storage stack our request flow from user space on the way to storage device. Okay, after and for user trace point, here we have totally have 4 latency or overhead. First one that is UFS at the FS layer. During this stage, for write request, if it's single mode, data buffer is allocated and memory copy is operation is executed from user space to cloud space. This exactly will cost much more time. For director write, it will directly go into next state. For reader, page checkup will execute during this stage to check up if data already in our page buffer. If already there, reader request completed and return. Okay, sync the state that is block layer and SCSI stacker and host driver. During this stage, for example, in block layer, we'll do our requester. Is our scheduler and plugger and unplugger and merge operation executed. Okay, before host in queue, when request from task into our storage device, host driver also will do, for example, bus buffer copy and DMM mapping. This will also will cost much more time. Then that will host driver trigger doorbell tell our storage device, oh hi, already there is a task or request in storage device. You should execute that. Okay. After data transfer finished, device driver will trigger harder interruption handling to do some requester poster routing. Okay, from this flow we can say there only may has 4. Then they say well exactly impact our request. Okay, that's. If you have some question about this, we can talk about in detail of meeting. Okay, now go back to Zoltan.
Thank you. Okay. Am I on? Yeah, okay. So basically, just to recap, we've broken down into 4 sections the storage stack, and we actually traced the execution time in all those four sections. Now, let me continue with the eMMC stack analysis. On this slide, you actually see a link. We do have a white paper on it. So if you're interested in this analysis, then you can freely download it. So let's continue with the eMMC. We actually used 2 boards. One is the Xilinx Zinc Z board. I'm not even sure what is the exact terminology for this board. And an NVIDIA Jensen TX1. One is a little bit older. It's a Cortex A9, 2 cores running at 667 megahertz using DDR4, 3DR3. 512 megabytes, and also running eMMC at the highest possible speed with eXT4. The second board is more advanced. I think this is an automotive board, Cortex A57, 4 cores, running 1.73 gigahertz, and 4 LPDDR4 devices. So you can see that the second one is, let's call it more modern board. And these are the 2 boards that we used in the eMMC stack analysis. Without dragging it further, these are the results that we've gotten. What you see here on the right side is the 4 I/O latencies. Each block here represents an average, and this is an average over 500,000 I/Os. We've broken down, you see 4 colors. These corresponds to the 4 sections that we described before. So 3 software sections, and the bottom one is actually the hardware duration. And then you have here on the y-axis the latency in microseconds, and then on the x-axis various workloads. So sequential read, direct sequential write, sync sequential read, sync sequential write, and correspondingly on the right side, the same thing for 4 kilobytes. What you can observe immediately and this is actually done on the Z board, okay? What you can immediately observe that, for example, let me take a 4 kilobyte example. For example, on a 4 kilobyte random write access, 88% of the time is spent in software. Okay? And only 12% of the I/O time is spent in the device. So, and you can see this across the board with variations, right? The smallest one is 63%. The highest one is 92%. Sequential write is always higher because there is a copy operation that happens and the page cache gets used. But what happens on this board is the Cortex A9 cache management takes a lot of time. There's a cache invalidation and cache flush that does result in this kind of performance. So, but I think it's a nice example to show you that when you talk about system level performance, it's not always the storage to be blamed. You have to look at the whole stack and you have to understand what's happening. Now let's look at the more modern Jensen TX1. As I explained to you guys, this is, the picture is a little bit better, right? If you look at the large chunk, 128 kilobyte accesses, the breakdown looks significantly better. Significantly more portion of the time is spent in the hardware, so the eMMC for the large chunk size accesses. However, for 4 kilobytes, you still have significant time that you spent in the software. Okay? Yes?
But that's related.
Correct.
Absolute total time.
Absolutely. Correct. So this is in this graph, right? 74% of the time is spent in the software.
I'm just thinking the overhead command timing should be the same independently of the current task.
For some reason I'm not exactly sure where I'm agreeing with you. We're observing something differently. But we should talk about it after, because I was also wondering about this. Go ahead. This is one thread. I will show you multiple thread later on I will show you, absolutely. That has absolutely an impact. This was our initial study. When I move on to UFS and NVMe, then we show you some multi-threaded operations as well. So in summary, the direct I/O has better performance as expected than sync I/O. There's a lack of memory copy operation and page cache usage. System overhead is observed to be a significant contributor to an I/O duration. Both more advanced and older processor systems. And this is especially pronounced with 4K or small chunk accesses. The Linux stack, does have, it does take up a lot of, it's not able to fully expose the underlying storage technologies performance, and I feel that maybe there's opportunity there to improve it. Okay, let's move on to something more interesting. How are we doing with the time? Okay, good. UFS and NVMe stack analysis comparison. I hope that the previous section made it clear, made the methodology that we used clear to everybody. So we applied the same thing here on the UFS and NVMe, and now I'm going to show you the results that we've received. The board that we had to use was different. It's a Heike 960, I think it's a Huawei chipset. It's A73, 4A73 and 4A53, ext4. The NVMe device is a 2.1. It's a 2-lane, 128 gig. Unfortunately, this board only supports a single-lane NVMe, so we had to limit ourselves to single-lane NVMe. However, we took a 128 gig drive as well, so that to make sure that at least they are the same in the size. I think I'm going to skip this because okay, I'm just going to quickly talk to it. Basically, this graph was one of the reasons why we started this whole project. The NVMe stack is significant. It's claimed to be significantly leaner. more efficient than UFS. So we really wanted to understand how much. I think I talked about it in the introduction. So let's see the results. In 4K random write, what you see now, we coalesce the three software sections, and we just, we said it, we're just gonna denote it with the color red. Not that red is bad, but we're just gonna use the red. So in a UFS with a single thread, now we actually used one thread and 8 thread, so multi-threaded operations were looked at as well. The red is the UFS software layer. The blue is again hardware, and you can see that here still there is a significant contribution from the software. It's not negligible. If you go up to 8 threads, the latencies are significantly decreased, right? So from UFS it goes from 100 and approximately 5 or 10 below 20, right? Because you're able to use the queues as well. Question?
Yeah.
Go ahead.
I'm pretty sure a big part of the difference you see between one thread and main thread is due to interoperability. And so more detail in that red part here, which includes actually interrupt overhead. Back to your slide.
I don't think we have the interrupt overhead. We
Well, if your picture you showed about your 1, 2, 3, 4 parts, you have the interrupt overhead in the completion pass.
okay. Yeah, we'll look at that. Maybe I'm not sure I understand the point, but we yes.
So from your graph, if I want my storage to move faster, I should run some threaded right in the background.
Yeah, I mean, okay, you can, if you run the threaded, if you run something in the background, if it's useless, you're not getting anything out of it, right? So if you run it, the storage performance is going to be more efficient. However, you're not getting out of it because it's useless threaded in the background. This is per thread. This per thread. So the storage actually, it has a queue, and if you're able to dispatch more commands at a time, there's more outstanding commands at a time, it becomes more efficient because there's there's NANDs inside that are much more, you can use them in parallel, so your storage bandwidth is actually increasing.
Yes. Storage bandwidth.
Correct.
But single write latency is decreasing.
No, but back to what I was just saying, for the multi-thread case here, you're basically running at FIDEPS 8, and most of the time you're going to get single interrupt that will signal the completion of 8 commands. So your interrupt overhead is going to an average for each command. So you get less overhead per command in this feature here. And same for the entire running the clock stack for each command, because you can pipeline a lot more stuff. So the overhead is split between multiple commands. So in average per command, you see less overhead.
Yeah.
Same as in networking. If you think of it, it's exactly the same. The more stuff you give the kernel to do at the same time,
The more efficient it becomes.
But it's like, if I want to speed up my networking, I don't start the download in the background, right?
Because it's useless, right? I mean,
It says
No, but, well, in the case of networking, it's easier to trigger a kind of high QDEPS operation. We're talking here of IOs, and it's explicit from the application. It's not stuff that comes from the network. So if your application cannot operate at high QDEPS because it's not doing asynchronous IO, for example, that's you're going to live on the left side of this graph. If your application can use asynchronous IO, you can run at high QDEPS. You're going to be on the right side. It's going to be much better.
okay,
yeah, let's postpone it after the Q&A. Okay, so you see that there's a significant improvement for multi-threaded IOs. The random write still suffers from a great deal from the storage overhead. And I must say, right, that inside the storage device there is DRAM or SRAM. And so the data actually gets written there. It doesn't go to the NAND directly. So even though this actually is rather small, but the hardware is very fast, and so proportionally the storage overhead is big. Okay, the picture looks much better for 128 gigabyte or 128K accesses. However, you can still see that the overhead is not insignificant. In some cases, it is 45%. For UFS is greater than NVMe. Now, you must keep in mind that the hardware here are not equivalent. Okay, the UFS and the NVMe that we used are different. So we tried to take away that dimension, and we tried to express this. We took exactly the same data that I showed you, and we tried to express the difference of the overhead difference between UFS and NVMe. So if I consider UFS to be 100%, then for one-threaded 4K random write, NVMe is only going to be 66% of the UFS overhead. So there's about a 34% increase. With multi-threaded accesses, the difference diminishes or decreases, right? There's only 20% benefit. And for random read, we go from 21% down to 4% for small chunk accesses. Okay. For 128K, the picture is, the difference is a little bit bigger. We have here 42% for one-threaded UFS and NVMe, 8-threaded. There is a measure. We just put the measure data, right? So there is 59%, and for sequential read, 74% and 62%. Okay, that's nice. But what does it mean in terms of user space performance, right? Okay, you showed me that there's a difference, fine, but how much is that going to translate into in a user space performance? So this is something that we tried to quantify here, and we could only do this theoretically. I explained we don't have two devices that are equivalent, so we assumed two identical. So theoretically, we assumed that there is a UFS and NVMe device that are behaving exactly the same in terms of performance and in terms of bandwidth, latency, sorry. So we assumed a write access time, sequential write access time of 128K of 150 microsecond. This assumptions is really realistic for a 128 gigabyte eMMC or UFS, right? So we didn't just take a number. We actually looked at the available devices out there, and we picked a number that is kind of representative. And sequential read access is 124 microseconds. Correspondingly, for random accesses, we assumed for random write 28 microsecond, for random read 80 microsecond. And then with this, we actually applied the latencies that we measured, and we calculated the estimated system level performance for NVMe and UFS for 128 kilobyte sequential read and write, and for 4 kilobyte random read and write. And what you can see here is, not surprisingly, right, we've showed that the NVMe system overhead is leaner, more efficient. So you get about approximately 25%, and this is an approximate number, with an equivalent UFS, with an equivalent NVMe device, you will get 25% better on a system level in sequential write speed. So in this particular example, this corresponds to about 120 megabytes. This is not negligible. For sequential read, we've calculated about 75 megabytes speed difference, again, to the advantage of NVMe. For random write, we measure the performance in I/O per second. So for random write, we measured about, what's this? It's about 3,200 IOPS per second, just coming from the fact that the NVMe is, the stack is better as it is. Remember, we didn't modify anything. We just took the board and we measured as it is, and we used those numbers to get these data to you. For random read, the difference is not as significant. It's about 8%. What are we looking at? 600 IOPS. So, not unexpectedly, we kind of try to show you here that NVMe in an embedded device will perform better than a UFS device. And simply coming from the fact that the Linux stack is better. And I'm not talking about the device differences itself. So NVMe is generally a better, is a device, a technology that has been designed for managed NAND media. The other thing we wanted to look at, and this is, I don't know how relevant this data is, but UFS has a queue depth of 256. However, with the current host specification, controller specification, the host side, the queue depth is limited to 32 tasks. On NVMe, this is, I think the maximum queue depth is 65,000 and something. It's a huge queuing infrastructure is spec'd in the NVMe specification. We did a simple exercise. We basically ran here a workload, a file workload with 2,048 threads, and we wanted to look at the queue depth. Or we wanted to look at the number of outstanding commands in the device. Okay, and what you can see here, this is the big picture, and these are the samples. We zoomed in here at the bottom graph. It's actually hovers around 31, 32. So most of the time we managed to push 32 commands down to the UFS, and we did the same thing for NVMe. The picture looks slightly different. As I mentioned, the queue up there is greater. So this is the zoomed in the bottom. In this particular device, there is 1,024 allowed outstanding tasks, and with a workload of 2,048 threads, as expected, you see that there are 1,024 outstanding IOs in the NVMe device. You see this behavior. We actually don't understand why this is happening. We need to evaluate this. Yep. Probably. Sorry? This is a synthetic use case. We wanted to understand what happens if you go over the allowed number of threads. I mean, I agree with you. 32 threads is correct. Yeah, correct. However, the use cases are changing very fast, and especially in automotive, right? So, sorry? Read. So, I agree with you. This is pushing the limit, right? It's a synthetic workload. It's in the lab. We wanted to understand the effects. However, I think in the future this will be important. And then I'm going to conclude the effect, we normalized the performance. So we actually measured the performance as well. And we wanted to see, okay, how does the performance vary in terms of when you increase the thread count? And you see the blue is the UFS. You know, it increases to 32, and then kind of starts to come down, right? And you have to go pretty high. I mean, you have to go 512 threads before it actually, loses 20% of its performance. But NVMe stays nicely flat. So it saturates and it nicely stays where it was. For high thread counts, very, very high thread count, NVMe is significantly, better suited. Okay, so as promised, let me do some summaries. We tried to, what are the takeaways from this presentation? I think the key one is that the system overhead is, based on our observation, is significant, and it eats into the underlying storage performance. You saw that. We've showed you for several boards. We showed you Cortex A9, Cortex 57 and 75, 5 minutes? I don't see it. Oh, okay, thank you. And I think this is another important one. As the devices are getting faster, this overhead is proportionally going to be bigger. So it's going to be more significant. Remember, we were using here 128 gigabyte devices. If you double it or quadruple it, the underlying storage technology gets faster. The system overhead increases proportionally. NVMe shows an improved performance due to the leaner storage system. We measured approximately, well, we estimated it to be around 25% in some cases, but in other cases is also not insignificant. And the last point is that NVMe provides a richer queuing infrastructure, and this has an observable benefit with high thread counts. And to conclude our presentation, in embedded storage, we started off with raw NAND, NOR, and moved on to eMMC, and now UFS is becoming mainstream. But NVMe is there. It's an upcoming storage technology, and it has its place in embedded storage, in embedded systems. And as we showed you, in some cases, it does provide a significantly better performance versus UFS. Okay, with that, we can start questions. We have one more slide? Okay. Okay. Let's finish up with this. Okay, no questions? Yeah? Yep.
So, in all your measurements, you use thread counts as QDIPs.
We actually, yeah, this is what I use. We use the higher thread to get the queue depth going.
So run your FIO with VIOH and rerun it again.
Okay.
Because your high thread count is basically hurts you more in terms of the cost of the thread switch.
Okay. But I would like to, we will do that. However, for single-threaded IOs, we show that there is a significant overhead, right? And quite frankly, personally, I wasn't expecting this, right? And we are eating into the storage bandwidth big time. And I think, our study is not concluded yet, so we should exchange emails and we